recording is really weird. So, what are we going to do today? Is building So what are we going to do today is building image processing units on VHDL and then in Python and then on a FPGA. Why I am doing this? Because it's I think an important topic. Not very beginner friendly, but I will try to explain everything. I'm not an expert also, so I will try to be fast and efficient while coding. The other reason is I tried to do it at first, as in this was my last job packet in my internship program. I tried to do it and I couldn't do it. Maybe this pressure of recording myself helps me to do better. And the other reason is Feynman technique. Maybe I will figure out the things I don't know really well while I'm doing this, while I'm recording this, hopefully. And at the end this might not work on FPGA or in VHDL code or in Python. Anyways, I will try. So let's first talk about the computer vision, how computer sees images. As you all know, the image is two-dimensional. So let's say there is a y-axis, there's x-axis, and they are separated. Each box is a representation of, for example, this is a grayscale image. In grayscale image, the integer range that can any bit can take is between 0 and 255, I think. And if it is close to 255, that means it's as black as possible. If it is 0, it's as white as possible. You can think this box's position as this is an image of an apple, and this is the, so it's very small, it's a tiny point. So this is wrong. I don't know if you can see it. Let's write it in the paint. And never mind. There is a site about this. It explains really well visually. It's better to explain it that way. God bless this guy. So each box represents how black that point is, and it's positioned in a matrix way. So how can we filter it? It's also represented in below, I guess. Is it? Yes. There are different ways of blurring the image. initially you may define a specific kernel, which is the size of the kernel may also differ. This is tree matrix. It should be square though, and it is preferred to be not the dimensions should be in odd number, not even number. There are different methods that you can apply. For example, 2 by 2 kernel matrix, but that's a different case. So how this works is, this is too small, I can't see it. So this is 82, and this is our kernel position. We multiply this by kernel's value, and multiply this by kernel's value, and multiply this by kernel's value, and we do that for all this 3 by 3 matrix centered in 82 valued box, and the result will be one integer number, and that integer number then will be replaced to that position 82. Yeah, that's it. For example, this averages, normally you have to divide it, so that divide the result by a certain number, so that number ranges between 0 and 255. But if the total sum of the kernel is 0, then 1, then you don't have to do that. So that's it about how computer sees the image. The interesting thing is how the video, I was when I first introduced by this topic, I was wondering, so what is a video for a computer then? Also the colored image and video resembles each other. Colored image is a series of matrices. One, for example, RGB, for RGB, one this matrix represents the red value, the other one represents the red and green and blue colors represents. How computer sees video is like, it's for a grayscale video, it's one, for example, x dimension, y dimension, and the time dimension. Each time there is a different matrix. There's a 2.2 different matrices each time. I don't know if it's clear, but yeah, there are good videos about that. For example, computer file videos. I recommend these videos. They are good.
So, are you a filmmaker or a content creator? And look,
yeah, this guy explains well. Watch this if you don't understand my explanation. Why? The other question is why we want to blur the image, for example. This is actually blurring, and this is also blurring if we apply this matrix. As you can see, the details are diminished, so we don't see sharp, we see less sharp changes between edges. Why we want to do that? Why we want to blur an image? I didn't ask that question while I was doing this project at first, but now I'm doing it. As it turns out, we blurred the image for a couple of reasons. One of them is let's see by an example. I did this before I start recording it. These are my example images. This is a famous photograph that everyone uses while processing images. This is a cameraman, and there are some dirt, let's say, on the image, and there is an original one also, clean one. There's another example just to test something. I put this example because it's so detailed and complex. Maybe I'll show you the code. First we import OpenCV and other NumPy array libraries, which helps us to do quick image processing. City image is this one, and cameraman is this one. This is the grayscale version. So if we apply a normal filter that takes the average, this creates a matrix, 5x5 matrix, which all have a value of 1. Then we divide the results by 25 to make it in range 0 to 255, and if we do that with NumPy arrays, we don't have to loop every box, let's say, address. It do that automatically. And this filter method applies this kernel filtering with the image that we chose. Image 1 was city, and image 2 was, what was it? This one. My image is this one. My image 2 is this one, so we don't use this one. Okay. So this is when we apply the average filter. This is an average filter. Let's see the result. The edges are not really clear now. Let me show you the original, or the grayscale one. We can see that at the same time with OpenCV. So imagine this is a grayscale image. So this is the original image, and this is after applying medium filter and grayscaling it. So let's continue. I will remind you again, I was trying to explain why we do this blurring process. I didn't yet come to that. Why? This is the original image. about the second one. So this is after blurring the image. You can see the dots on the images seem less obvious. This is one of the reasons why we may want to apply blurring to reduce the dirt, reduce the salt, they say, on the image. The trade-off is the other things like cameraman's face is not obvious right now. This is a trade-off, but it is possible, I imagine, to apply this thing outside of this certain addresses. It is possible, but again, you can't select individual addresses. It would be too much work. Maybe artificial intelligence, machine learning processes may help with this work. The other is, for example, edge detection is an important concept in, again, machine learning. I remind you the first image. This is very detailed, and let's see again, second time, what happens after we apply medium filter. This, we don't see shit. Like we need the glasses. Yeah, that's what happens. While detecting edges, what do you think will happen with this picture and with this picture? If we consider by on our own mind, let's figure out the edges. Let's say we see this one, we can see the edges, but now we don't see all the edges, we see some edges. For example, this is still a clear edge. This is still a clear edge. The round road and the lamp maybe still a clear edge. Bridge is always a clear edge, but I can't recognize the edges inside this region clearly, but I can see that in here. Let's see how edge detection may work with both of these pictures. Okay. So we are dealing with this one. Yes, this. No, the other one. Let's see. This is a function that we can see edge detection. Which one is this? Yeah. This is the first one, I think, and this is the second one. No. Yeah, this is the second one. This is after blurring the image. We don't see a lot of details in this one. For example, we can still see the bridges. You see? We can still see that like mosque-like thing. Can we see the lamp? I can't see the lamp, I guess. This building is clear. Let's see again. Which one? This building is clear again. This building, and what else? I should have seen this, but this is probably it, but I'm not sure. What about this bridge? Yeah, it really looks bad. Let's compare it without blurring and applying edge detection. This is application of edge detection without blurring. Let's see. Let's make it sure. Yeah, this is the first defined thing. Yeah, this is not blurred image. Let's see it. Yeah, it's much more detailed, but we see a lot of things. We may not want to see a lot of things. Why we don't want to see a lot of things? How can I explain this? For example, you are writing a program that detects faces, and you know the zoom program which blurs the background, and it has to recognize the edges of the face. If we don't apply blurring, for example, yeah, a simple disturbance would, it's really hard to explain visuals with words. We apply blurring to detect more hard edges, let's say, more important edges. If we don't blur, we see all the edges, and we don't want to see all edges. That may confuse the machine learning algorithm. That's why we need to blur. Maybe that will explain clearly. These examples also not selected clearly. They should be selected more important, more explanatory. Anyways, that's why we apply blurring. Let's start with writing VHDL code. If someone explains or teaches you any hardware description language, Verilog or VHDL, they really like to the teachers really like to emphasize on this. Hardware description languages are not a programming languages. So what you need to do is think about the circuit in a solid form. For example, loops are not something casual you can use on Verilog or VHDL. Loops are just methods that you can use to quickly write the code. Not yes. Hardware description languages are not programming languages. Know that. That's why I'm trying to build the circuits in my mind first, what we will do, and then we'll start. Why I'm writing on this software program? because it has better syntax check on VHDL than VS Code's extensions. Also, you can quickly run simulations to test whether the program works in your mind. Before that, let's think about the circuit. What we will do. I'm drawing the image right now. Let's say we have image like this. How many lines? It doesn't matter. Let's say this is the 0, 1, 2, 3, 4, 5. Let's draw more. 6, 7, 8, 9. This is arbitrary, you can do whatever you want. This is a very small image. Just think about the process. What we will do. And it goes like 10, 12, to 20. 11, 21, like this. So, for example, we are considering this box. We have to take these values, each have a value between 0 and 25. We will take these values, for example, let's say we are applying minimum filter, which is we will take the minimum value inside this 3 by 3 matrix. Let's say this is 15, this is 11, this is 78, this is 88, this is 100, this is 101, so 102, 103, 100 for really imaginative. So this is input image. What will be the output? For example, for address 11 will be 11. Yes, what a coincidence. This this is because this is the minimum, and we are applying minimum filter. Minimum filter. The thing we can do is, you know, maybe later in the future we want not to apply minimum filter, we want to apply maximum filter, or we want to apply mode filter or medium mode filter, yeah, which takes the minimum number when we sort the things out. So the all 9 numbers, and we take the between them, 5th one. That's why it is better to do it with sorting. First we need to sort these bits, and then we will take whatever we want. We can then apply minimum, maximum, median, not median, mode, yeah, whatever we want. So what we need to do is we take these bits and sort them. Yeah, like this. It goes on like this. There are different sorting algorithms we can apply. We can apply any of them, but I am advised, while I was starting this project, doing my internship, I am advised to use which one was it? Which one was it? I forget. Selection, was it? Yeah, I'm advised to apply selection sort algorithm. Why? Because I don't really know. I don't really know why we apply this. It might be because, let's say, we are doing this one next. After 11 we have to do this 12, address 12, and we will still have this most of the same bits, and we will add these new 3 bits. So when a new value comes, let's say x, when a new value comes, these are already, this is the intuition, I don't agree with this, but we already sorted this, so we just need to add this one into some place. This is when we add another value, we can just deal with this and put that with comparing. But in my opinion, maybe I'm doing this very inefficiently, but I think the registers are cleared, aren't they? Maybe they are not cleared. Anyways, let's apply sorting. This is the algorithms we will choose. Selection sort. Anyways, we will sort the numbers, and we will take, if it is a minimum filter, as we first initialized, so we will take the 0 one. If it is maximum filter, we will take the maximum one. If it is a median, then we will take this one. You can, yeah, modes or median, always mix them, min, max. The other thing we should consider is, can we make it bigger? Other thing we should consider is how these addresses are related. This is this is a very headache causing problem at first, but now I figured it out. It's really simple actually. So if we have, let's say this is x, what is this to this in relation to this? Minus 11? No, of course not. This, for example, for 22, this is minus 11. Is it minus 11? Yes, it is. Yeah, minus 11 for this. For if x is this and this is minus 11. What does 11 come from? 11 come from, let's first think about the top one. Top one is just going one column back. This is one row back. And how many values does the row have in our arbitrary image? 10. Then we have to go up 10 addresses back to reach the top value. So we will say top left, top right, left, right, self, right, bottom left, bottom, and bottom right. Row number, let's consider it parameterized. Top left, how do we reach top left? How do we reach top? Any specific x minus row. In our case, this is 10. Yes. How do we reach top left? Top left minus x row plus 1. Yeah, we did. And continue. Is it correct? The important thing again is edges. Edges don't have top left. For this edge, for example, doesn't have left things, boxes, addresses, whatever. That's an issue. That we can ignore it. It's possible to ignore it. It's possible to ignore it, except that, for example, maybe 0, because you cannot go back address because there's no address in -1. It will cause problems in VHDL code. So we will try to avoid using this. Why I'm saying this, we can ignore this, because when we're dealing with huge image, this one tiny bit may not be very important, and we can consider this one, this one, this one, and we can consider which one? This one. The filter for this border address will take this one, this one, this one, this one, this which one? This one, this one, this one, and probably this one. Yeah, and this one for this position. It might not be very important. I don't know. Since this is my first attempt, I will ignore it, except these top and least bottom ones, because that will cause problems. The code may try to find the value in this address, but there is no address in that position. So yeah. Did I miss anything? Rows, columns. What about columns? Do we care about columns? Is it important? Is it important? I don't think so. I don't think so. This is just addressing part. Now we have to think about circuit. And we have to think about different modules. Why? Because it's easy to debug. We can know where the problem is easily. Let's assume there is a control module. Control. This will control the modules. This is disgusting. This will be our memory. Memory will store the address, and we can create another. For example, memory read. This will read the memory. This will output. Right. Right. Now we can think about columns, because we are thinking about the size of the memory and addressing of it. Let's say we have, it will probably change during coding, but let's say we have rows of 10 and columns of, how about we think about, we continue. Columns of, how many columns do we want? 10 is too small. Let's say 100, and let's say 100. It may be too large for memory, but let's we think about later. 100 and 100 square image. This will take address input. This will give data out. We will give data in here. What else? Clock, always clock. There's always a clock. Since we will sort it, we need to sort the information, and the memory read can only give one address per one clock cycle. We need to store these datas before it becomes 9, so that we have all the 9 values, and control values will give the addresses in a appropriate address. For example, for this address, the control unit will give this addresses of these boxes. It's inside, and data out will be stored in somewhere to send sorter. Let's create sorter. Let's create a memory interface. Why? Do we need this? Do we need this? Do we need this memory interface? Do we need this memory interface? Actually, we may not. We may not need it. Let's think about it. It may make it easier for us to understand. That's why I like to add memory interface. We may not need it. We may not need controller also. If you apply this design perfectly, you don't need the controller. These are just steps to make design easier to debug, maybe, and then you can do it second time. You can just delete this if you want. Memory interface. I will add this. This will store 9 is it bits, bytes, words? I don't know. Data. Then gives the 9 data to sorter. Then have 9 data, can output 9 data. It is possible, but we are thinking about, since we are thinking about 3 filters, median, mean and max. We can even adjust which one we want inside by a mux filter mode. This is insights. Yeah. So this can give one output. It takes 9 input and it will give one output. This one output then be our new image address. It seems simple now. I think there might be some other things. It shouldn't be that simple. I mean, sorting algorithm inside this is hard, but is that it? Timing is an issue. Just take 9 data and we have 1 data. This will give this one data out. Of course, this also have clock. One sorter. Takes 9 inputs. Takes 9 inputs. Selects medium, min, and max. Puts. We have to. This address, we have to remember, store this address in somewhere so that we don't give it the wrong destination. This is important. We take the minimum, median, and maximum of this kernel, and we store that value to here in an output memory. we do that the same for every other box. Can we now understand why we're using this algorithm? I mean, you need to reset the registers in here, so you have to sort it again anyways. It doesn't matter if you just use another sorting algorithm. I don't think it's important. So what else? Address in is important, address out is important. Out var. Bir de tabii ki de image address out. Yeah, that's it. Filter mode var. Clock, there's filter mode. Okay, I think that's enough for now. Controller, memory interface, controller memory interface, sorter, I wanna see my previous attempts. Did I do anything different? Do I have any other? I added this module in my previous attempt. This is useless, I think. We don't need this. Yeah, we don't need this. It might help with seeing the output clearly. It might help with that, so that we can see all the it can be done later. Controller, sorter, and then we need memory interface, and we will need top Testbench. will explain this, what these things mean in a second. What I'm doing, it's not really complicated, it's just syntax. How many addresses do I need? How many addresses do I need? Controller. So the other thing is, we have to also have a tag for each addresses. So this memory interface will have 9 different data, but we still don't know which one is which. It doesn't really matter, we just need 9 data. But I want to add another thing so that we can follow up with simulations easily. Position. How many do I need? Let's say integer. Just follow it correctly. Integer. When you do this data type, it inevitably have 32 bits, so you should avoid this kind of style, but it helps now initially to understand what we're doing. Characters also, I guess, 32 bits. So this just kind of position tag. What else do we need? We need others out. What else do we need? We don't need anything else. We can take a signal from memory interface that 9 data has finished, and we can start the sorter with controller. It is possible, but do we need it? Or is there another way? Or is there a better way? Yeah, how can this thing know that specific 9 data has been finished? Okay, this gives 9 addresses, but how do we know? How does this thing know that it should start a new cycle? So there should be a connection about it. but the signal I give can position out, can do that job. It will take values between range 0 to 9 likes, and maybe 1 to 8 anyways. This is how we initialize finite state machines. We will drive a process. We'll create a process. We'll create a process that will change, that will depend on our current state. Like things like I was talking about why hardware description languages are not programming languages, and we should first think about solid version. It is also the case for, I think, finite state machines also. You have to think what are the states, what is the outputs, how will this state changes before writing the actual finite state machine. But not doing that. These others, sometimes there's a problem, so it's better, it's a good practice to write. And others, this is when controller state is in different states than these defined states. How the status will change. You can define a timer signal. Timer integer. It's also possible to create a variable, but you can't follow up the timer in when is a variable in simulation. You can't follow up the W's. Also, it's really not well things to do. We forgot about addressing, how the addresses will change. That is more important. Why anyways. Let's first addresses will change and give the appropriate address, also the pointer. Another finite state machine, which gives the kernel position states. It can be initiating. We need it. Initiate. Yeah, we need it. Why? Because the memory block needs a couple of seconds to work. Initiating top left, top right, left, self, right, top left, bottom left, bottom right. Is that all? Do we need anything? I think it's enough now. Bottom right. Yeah, we also want to have a just state. Why? We will see it later. Kernel control states. Position state initiating. This is the actual signal, not this one. This is like, now it's like a data type. These positions are not right. We will figure that out later. I'm now writing useless stuff. Not really. I don't really need my brain, I guess. It's a meditating experience. There's a cool thing you can do with this text editor. You can press controller and do this. I try to find the same thing with VS Code, but it works different. What is this semicolon? One thing I should mention is we will need to add block RAM memory IP. What is IP? IP is an intellectual property, but it doesn't matter. There are certain built-in modules in FPGAs. For example, block RAM is one of them. Block RAM is just memory. Of course, there are multiple registers, a lot of registers inside the FPGA, and you can use them, but it will be all over the place. So when we are dealing with huge data, relatively huge data, of course an image is a small data, but for a digital point of view, an image is a huge data, so we have to use this. For example, what we said, 100 to 100, we said 100 to 100 means a lot of data. A lot of data. So this IP, intellectual properties, helps us to use those block RAMs built in FPGA. Without doing it. Otherwise you are using registers inside the FPGA, like single flip-flops, like yeah, this is now we have to think about this. What we have said 100 to 100, we said. I want to test this with the actual image. That's why I am looking for real image. I designed what would you say, library module in Python that you can figure out how many bits you have on the image, and also the shapes of the image, y-axis, x-axis, and it also creates a file which can use to import on this block RAM. We will need to initialize the block RAM for the actual image. But the thing is, you cannot just import image in this version. You have to import a core file. Core file is similar to text file, and each data is separated by comma. So we have two-dimensional image, but we each have a x and y position, but we need core files, we need like one dimension. So how we will do that? Each row is put first, then the second one starts. This is like one row. This is second row. Of course, you can do it other ways. You can do like a diagonal. It's possible, but it will be complicated. You don't need to do that. The important thing is you have to know which address represents which position. You have to keep that in mind. Otherwise, you can do whatever you want. So we are trying to figure out how many addresses do we have on the so that we can initialize the block RAM. We will import my library. We need an example image. We can work with this, I guess. It will be. Is it good? Is it too light? Is it too big? It may be too big. Again, for an FPGA, it's. This image was cool though. Is this good? Is this good? This looks like Sonalica. I think this is small enough, is it? I wish there are smaller ones. Very tiny image I'm looking for. This is all very large. Stupid shape. Okay, this is good enough. For this you have to put the address of your image if you are using this class. Name of the images. This is the directory of the new file which will be created. Desktop is fine. You have to put true in this. And then we have to apply the methods of build code to build code. What else do we need? Do we need anything else? I don't think so. My test image starts. Will I see the shape of it? Let's see. Maybe. Your image shape, yeah, I can see that. You don't want colored image. Press 1, yes, 1. What is happening? Is it created? No. Again, we run again. I'm sure it works. Yes, I don't want colors. What is the maximum number of address in bram? Let's see. Maximum number of address in bram. Right, depth 100. We didn't. This is not appropriate. You have to build a text file. I was wrong. Text. Don't want to memorize this number again. So again, like this shit. Yes. What is the maximum number? This is the maximum number. It will check if it is larger than that or lower than that. I think it's not larger. Let's calculate it. 565 multiplied by. Is it larger? Of course it's not larger, it's smaller. Checking if true. Yes, I was wrong. This is the thing we should input. Oh, it's very small. It's good. It's small enough. I mean, to check if it is, if my library did its job right. We also want to do the reverse. It's better to do that. Let's try that. My texts. equals. This is the second class. There's only two classes anyway. Dir code dir transform to image shape. Do we remember the shape? Yes, we have to remember this shape. Sometimes it may be a problem. Again, okay, this is it. This is a boolean. We have to say true. What is the code directory? Code directory, you can just copy this. Code directory. And what is the direction of the new image? New image that will be created if I wanted to. I am not wrong now. So my text dots create the image. No, you have to first do another thing. What is it? Create the image, build array. You have to first build array, then my text will create the image. It. Let's see what will happen. I hope it works well. Coder, this is coder. Yeah, I was wrong. I was wrong. Dot text. I was wrong. Dot text. Code dir transform shape true. I am not wrong now. Dot jpeg. Maybe this was wrong again. I don't see your point. Yeah, it should be a stupid mistake. I hate this when this happens. Maybe the code was wrong. Maybe the columns are not in right slope. So the first one was right. Jesus. Was this one was correct? The opposite of this, you see? Opposite of this one. This one. this one, this one. This one. This one, I was wrong. The text JPEG build array. Let's say PNG. Text to none. This is the text. It was wrong. It wasn't wrong. I used the functions wrong. So you have to do this, and then maybe build array. Let's just build array. Folder. Should I increase it one volume? will check this again, come back later. So I come back, I found the problem. Somehow you need your text files should not be started with capital letters. I don't know why. That was the problem. How could I know? How could I know? So let's do it all over again. By all over, I will just try to build a core file to import on memory, block RAM memory on FPGA. Let's pick our image. This is our image. No, this wasn't the image. There was another image. What was the image? No, this one, not this one. What was it? Was it? Yeah. This is smaller. This is smaller. This is better. This shouldn't be here. And this shouldn't be here. Okay. My test image. What the fuck is this extension? City. The direction of the images or city JPEG. City JPEG. New item. Okay. Run this. This image is colored. Should I fix it? Yes. Maximum address bram. It is I forget it. This number. What is this? What is this? Anyways, I'm not worrying about it. Our core file has been formed. Now I want to see if this text file actually same as this image. So to do that, I want to apply my second function, which I built previously. Text num codir is new item dot text, or let's say new image. Dimensions. What was the dimensions? 500. Yes. Build array, create image. Let's do this now. Desktop, new image. Okay. Specified location. Let's see if it is. No, it's not the same. What happened? What happened? Erased. Something happened. Something wrong happened. Awesome item. Maybe I didn't do that. Maximum number. What is this? So maybe I did dimensions wrong. Oh, this one. Is it your image shape? Yeah, this is my new image shape. Checking if the image is, yeah, awesome item. Now again, this has, let's check this text file is the same as this JPEG. Again, for the last time. Let's not forget the shape. This is our code directory, and this is awesome image. True shape, this is image. Let's run this code. Awesome image. Yes! At last! At last. You see, this is the same. There are some kind of errors. I don't know why this is occurred. There are some things I don't know in probably this. I will blame OpenCV. These dots. So this transformed into one-dimensional array with the function that I used, and then I check if this text file is the same as this image, and I again use my another function to do that. These two functions, and it created the new image from the text file. Only errors are these stupid dots, and I don't see anything wrong. We can continue now. Other thing is, how many addresses do we need? Yeah, why we started this at the first place. We need amount of address multiplied with y dimension with x dimension. Let's put that right depth 269440. It's larger than the maximum. It's larger than the maximum. No, it won't work. It won't work. This image would not work. I will build another. I will select another image. Tiny image. Animal icon. Tiny image. Single one. How can you blur this? This is irrational. Small image. Can't I have more options? Like this small, like this small. This could work. This is still large. This could work. Or city image. Let's do that with alpha. Let's see. checking the size. Checking the maximum size. It's enough, it's good. You can use that. I can use this one. Oh, too large. This is better. This is square also. This is good. This is good. I will run the codes again. Fix it. Yes. Don't forget about default value. Again. This is the same. Location forms. Let's do that in this form. Yeah. Let's change the shape. And if we don't change the shape, it will cause problems. Believe me, it will. It's awesome image. Let's check. Awesome item, city, awesome image. As you can see, it works really bad. I will pause the video, I will select a good picture. So I find the image, I find this one suitable. I created the core file with code and I tested if the image is right. Is right enough. So I close this. The dimension is this. We need to not forget about this. And we can close this. We can close this, close this. Now we can load. So this is multiplied by x and y axes. We need this amount of addresses. We now load the core file. It's a text file now. I'll change it. Text file. Let's change it to core. Yes. Now it will work magically. Yeah. Can do this. If there's any lines. Yes. Why it don't work? Because I read the code wrong. It should do this. Still wrong? What? I changed it. Okay, I'll do it again. Yes, yes, yes. To represent 0 to 255 we need 8 bits. 8 bits. Now we load the init file if we can. Now yeah, there's 2 1. We didn't change this one, we changed this one. Okay, now since this will take time, I don't know why. It just uploads a small text file into a memory, but yeah, I will pause video. Okay, I am back. I checked the sound. I fixed it. Now let's talk about what we have done so far. For the first 1.5 hours, we describe how can we reach certain addresses that we want, and why these positions addressing can be related to each other. How can we represent a single image bit, and how can we blur it? We talked about this. We talk about different filters, minimum, median, maximum, and we build a controller that gives certain addresses around a central image bit, and also it gives a tag to it gives a tag. Why it gives a tag? Because we can follow up with the simulations which bit is where is the signals are driving correctly. We can check that more easily. Also, we can understand that we finish the circle by checking the tag. For example, if the tag says kernel positioning tag is 8, then we can say the one circle has finished, and we can go to the next central image bit, which is driving in determined in this adjust case. We just upgrade the central address to 1 next until it reaches to the last column, because if we don't do that, the filtering won't work correctly. Also, these edges, these corners are really dangerous, because we want to access the addresses around that central image bit, and if we try to access -1, it may not access that address because it doesn't exist simply. But since we are dealing with integers and turning it to unsigned, maybe I imagine it will try to access this bit, so it may not cause any problems. But let's just do that for now, and we are starting our initial central image by 361, because the image we have chosen has the dimensions of 265 in y dimension and 360 in x dimension, which means amount of rows. So we did that before. Now we have to match this kernel position tag with the image bit which comes from the block RAM. Also, what we have done so far is we define a signal timer. This timer with the help of this timer, we can give kernel position tag 2 clock cycles after we give the address to the bram from the controller. Why? Because you cannot take the data out immediately after giving the address. You have to wait 2 clock cycles. where does it say? You can just check block design. It says in the while you're creating the IP block, it says you have to wait two clock cycles after giving the address. So we are doing that. Let's check. Summary. Total latency is 2 clock cycles. That's why we are giving the tag after 2 clock cycles. We have given the address to the bram. We have to do the same for writing also, I guess. Yes, probably. So we can start with memory interface. We have clock image bit, which comes from block RAM. Kernel positioning tag comes from controller, and memory interface ready is just an indicator that we have finished the first cycle. This memory interface will give 9 image bits to the sorter, or can just give one. No, it says 9 data. So we want to give 9 data to the sorter, and sorter will sort the datas and give our desired result, whether it's median, minimum, or maximum. It's possible to do that with this, for example, image top left, image top right, all STD logic vectors with the same address length, but there's a more cleaner way to do this, which is building our own data type, I guess. I don't know if that is it. So to do that, we create another VHDL file. Let's say my data type. To use that package, we need to add library work and use work all library. Okay, but we didn't build a work and our package, which is my data type. Okay, so my data type. I forget how to build. So I will check my previous attempts. You say packages, my data type is array image. This is an array. We simply define a data type called array image. An array image can store 9 amounts of std logic vector, which has 8 bits depth. Okay, when we save, it will disappear. That's how Vivado works, for no reason that I can understand. So now we can use this. Let's say image array to sorter and array image. Was it like this? Array image. What is this? Yeah, it works. This comes from bram. We will build this, and this is important to do that. I think we can't use this directly, so let's try. Kernel position tags tag 110. On beer 11 comes when we are in adjust stage. So, and now we can fill this because it's an out signal. We have to define another signal, then we make it equal to each other. Okay, so since it's an array, we have to do this. And what was the this is the input from bram. Okay. Do we need anything else for memory interface? No, we didn't make it. After that we can give this filled array image to the off signal because it's now ready. Okay. Yes. Okay. Let's build our sorter. Sorter will also have this, but this is input comes to sorter, but we didn't use the work library. We will also need numeric sorter. What does sorter need, please? This 9 data is our array image. This array image. It has to take the filter modes and clock. This is in. Does it need anything else? We can start the sorting process with the memory interface ready signal. So we can memory interface ready. We can put this in here. This can also come from controller, but why we would do that? And sorter will give our new image bit. This is a CD logic vector. Has the address of 720. do we need this final state machine? We could do with if statements, but cases are better to follow in again simulations. So I also want to deal with internal registers, not with the input signals. When memory interface is ready, then we can fill our array with the inputs, and we can change the states to sorting. These can be done in rising edge. And sorting begins. If rising edge work, and if I don't know how many clock cycles do I need to finish the sorting. That's why I can't just do that. It will be a loop. Let's just forget about that, and we should build a sorting algorithm here. What was this algorithm that we should pick? I forgot the name. Selection sort. We will use selection sort. Okay. We would need a variable. Variables are written in between process and begin. You cannot put a variable here or here. Variable. Minimum index integer start with 0. Okay. We need 4 loops for E in range 0 to 9898. And loop for E into loop and loop. For E in 0 to 0 loop. Zero, 8. Is it 8? It depends on the kernel size. But our kernel has 9 data. So maybe we should just put an indicator. Sorting algorithm. It depends on kernel data -1. Num depends on kernel data -1. So we have another loop for j in I -1 to 0 to I -1 loop and loop, and if variable old std logic vector get it 7 down to 0. You'll need this later. If image array sorter, if image array sorter E or G is smaller than image array sorter E, then and if minimum index is variables are like this is j and min index is e, is j, and for each loop, if that is the case or not, we replace min index holds a min index this one and what no this one and this one is this one maybe okay this is like this let's check it. Oh no. I hope it works. I hope it works. And hope it works. Okay. Sorting. How many clock cycles is needed for this loop? How many clock cycles is needed for this loop to finish? How can I know? Is it one? In my opinion, basically, for every comparison to happen, there should be a subtraction, which is the same as addition, and additions or subtractions can happen in a combinational way, so this process can happen in one clock cycle, or even, but we're always doing these comparisons in everywhere. How these things work. I never thought about that. For example, this if statements don't need time, I think it needs time. Maybe it's inside the description languages interpretation itself. Anyways, I don't want to think about that right now. So we will test it and find out if we need anything to fix it. After that loop, our image array sorter is a sorted, must be sorted array. So if after this sorter ready. After this we can say, yeah, we can say sorter ready, sorter ready, and case sorter ready. What should happen? We should pick if case filter modes, case filter modes is when 0 0 1 0 1 1 1 0 1 the output depends on this. It is our sorted arrays. This is minimum, right? Controller filter modes. I didn't specify it. Let's say there's one min 1 max 1 median, others are nothing. 0 8 4 this is nothing. let's say this is also minimum. Also if rising mod, rising edge, let's assign sorter ready. Initially, it will wait for memory interface ready signal, the sorter module, and then when that signal comes, we will fill our 9 depth vector registers with the input which comes from memory interface. We will fill this 9 registers with 9 data comes from memory interface. We will store them with the ready signal comes from memory interface initially, and then next stage comes, which is sorting. It will happen, I imagine, in 1 clock cycle. We will sort these from minimum to maximum, and we will go to the next stage, which is the selection of the output depending on the filter mode, which is determined by controller. Our image array is already sorted, so if it is minimum, we can take the least one, 0, and if it is the maximum filter, we can take the largest one. If it is median, then we can take the middle one, which is 4. And after the clock cycle, we can go back to the idle states and wait for the memory interface again. And after memory interface is ready, again we do the same sorting again. That's why I believe we don't it doesn't matter which sorting algorithm that we use, because we are at every cycle we need to sort these new bits anyways, so why would we? There's no possibility that we can use the same data. Maybe there are, of course there's a possible better ways. This is the most simplistic ways that you can do this. We should keep in mind that why we are using selection sort, because actually we don't need to sort every 9 data for every changing central address. No, we just need to get those 3 new datas, and we can sort that, and it will consume less power, it will take less time, less combinational time, I don't know, it will take less time, but in very simple ways we are always sorting. There's 9 data that comes from memory interface, if it ever works. Okay, this is also finished. Controller is finished. I mean, not finished, but So I think we can test it now. I think we can test it. Entity, can say there's no port and main. We will add these entities as components, but first we need architecture. What? Begin and data flow and data flow. Main testbench is testbench. What do we need? We need process. Begin and process. What else? We need components. Components are here, and we need signals. Let's see. First, add the most certain one. Make it component. And component. Do the same things for this. Components. What happens? We can make it. Can make Testbench also generic. And controller, memory interface. Memory interface, controller, bram, main, testbench, sorter. Why didn't we use generics in these things? Why? We don't need it, guys. We don't need it. Okay. Now the signals. What are the signals? There's clock signals. There's clock signal. There's filter mode signal. There is sorter ready signal. There is memory interface ready signal. What else? We need image bit signal. We need image bit signal, which which is this. We need kernel position tag, kernel position tag integer. What else? Now, image array to sorter. Image array to sorter. Is data type. Image array to sorter. Image array to sorter. Image array to sorter. Image bit. Image bit. This comes from here. Memory interface ready. Image bit clock filter mode sorter ready. Clock image bit in image bit. You can say image from bram, same as this. Initialize clock with 0. Filter mode start. Signal start. Start. Address out important signals. Signal address out. Address out this size. What else? What else? Address out comes to address in blockgram. Which one do I need? Let's see. I don't need this. I don't need this. I don't need this, definitely. I used it with different name. I don't need this. Enable, write enable is important, but I want write to read bram. That's why I'm deleting that. This is write bram address. I didn't write that into bram code yet, but anyways, let's say bram signals same as this, just length. Right, we don't need write clock. We need this. Right, bram data in. Data is this length. Write bram data out. No, we don't need this. Right, bram enable. Yeah, we can do that. Bram write enable. We definitely need that. they will be 1 for now, always. Initialize as 1. Initialize as 1. Initialize as 1. Okay. What's your problem? Okay. Now we will define a clock. I am cheating from my previous attempts. What was it? Main. Sources. Main. I like to define the clock this way. Always. Signal, and where's the clock? Where is this? Is this here? No. Is this here? Yeah. What? Where should I put it? This. Now we need to match the signals with components. How we do that? We do this. We do that. We have to give a tag. We do port map. If we don't have generic, we put our initializers. We put this arrow, not the other one. Again. Then we match the signals. Clock is clock signal. Filter mode is filter mode signal. Filter mode signal. Memory interface ready is memory interface ready signal. Image array to sorter. Image bit. Let's first do controller. Generic map. Port map. Generic controller. Just copy. Do that. Do that. Since I defined this at the top of the test bench, it will match itself automatically. So I don't have to define what are these. These are already defined in this section. Globally, the word is globally defined. Of course. Clock is again clock. Filter mode is again filter mode. Start is redefined as start. Address out is, I don't remember. Kernel position tag is kernel position tag. This is the end of controller. Okay. Interface. 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 Code map. I need to go to bathroom. Okay. Okay, is it still recording? Where were we? Channel position tag. Interface ready. Generate sorter. Generate sorter. Image bits. Let's do that for bram. Bram wrapper. Bram wrapper. Port map. Bram. Now, controller gives the address out. What is the signal I defined? Address out. Address out comes from controller. Controller address out. And this is address in. Clock is clock. There's one clock. There could be multiple clocks, but I don't want to deal with that. There's again one clock, clock, and bram data in. Doesn't matter. Can we leave it empty? I don't think so. Okay, can we leave it empty? What happens if we leave it empty? Let's just do that. Write bram data out. Yeah, write bram data in. Write bram data out. No, there's no write bram data out. Write bram data address. This is actually the same with, if you can believe. No, it's not the same, but it doesn't matter now. Read bram write enable. Write bram enable. Let's do this. Where can I put this? Read bram enable. Read bram enable is fine. What else? Write bram address. I defined. Write bram address. I defined. Write bram data in. Write bram data in. I defined, but I didn't adjust it in the actual code. Write bram data enable. Write data. I guess. Okay. Read bram write enable. No. Read bram data out. Read bram. This is important one. Image bit. I said this should be image bit. Image bit. Signal image bit. Bram. Bram. Same as this. Image bit bram. Okay, this is better. I already defined it. Image bit. This is data out. bram right enable is current type still right bram right enable. Right bram right enable is a STD logic vector DK. It is it? Yes, this is stupidly STD logic vector. Because why? Because you can I don't know why. I don't know why. I tried to explain it to myself, but no, useless. So how can I? Is it? Yes. Also, this is also this right enabled. Right bram enable, right bram enable, right bram, right enable. This is now a STD logic vector. Right bram. Let's find this. Is this the logic vector? STD logic anymore. Why are you giving me this error? Type error near right bram enable current type STD logic type STD. Expected type STD logic. And not all of it. Yes. Bram right enable is vector and enable is STD logic. Enable is STD logic. Why? I don't know. There must be a understandable reason. Right enable, this is also this then, isn't it? Yeah. Do we have problem now? We actually need to define this and this and this. Right, and data out. I don't care. I don't care. This 0. Enable is bram enable, bram right enable is 1. Actually, bram data out, doesn't matter. Bram data out. This is useless. What else? What else do I need? Image array sorter. Did we define image array sorter? We have image bit. Image bit comes from. This is important. Here. Image from bram. Data out. This comes here. Sorter ready. Sorter ready. Image array to sorter. Image array to sorter. Image array sorter. Okay, this is also finished. Image array sorter will go sorter ready. Sorter. Sorter ready. Out. Logic ready. Sorter ready. Image bit. Image from bram. What is your problem? Let's check sorter. Sorter ready. Sorter ready. Now, do we have a problem? Sorter ready. And sorter ready. And it's fixed. Now we take this image array from array to sorter comes from memory interface. Yes, this is output, that is input, that was input. Image bit memory interface. Memory interface comes from image from bram. But we made a mistake. This is sorter and image bit is not image from bram. It's image bit. Let's say result. Okay. Let's see how many problems we have. Let's check. If I have no errors, even that is a success for me. In my first attempts. I think it's happening. No errors. No. I lost my hope. I had hope. Sometimes it stucks, so I will just restart it. I fixed these errors. Okay. Where is that sorter ready? Sorter 91. Sorter 91. Sorter 91. I fixed that to sorter. Okay. And there's one more. I fixed that to sorter. Okay, are you happy? Are you happy? What is this? Why don't... What is this here? Doesn't have a meaning. I don't remember that. Maybe I was testing probably to unsigned operator methods. Okay, let's try again. The thing we also will need in future, taking in the inputs and actually testing if the filter has happened. Even though there is a write bram, the simulation doesn't actually write the results. So we have to pull that signal out and check. Channel position is initiated in wrong, so we can change that. Channel position, that's important. Channel position has to start with 0. Then otherwise obviously there will be problems. Can I see another mistake? Clock's not working? Yeah, clock is working. Okay, let's try again. Okay. Image from bram. We can kernel positioning is not updated. Kernel position main test bench. I updated it. Main test bench kernel positioning is 0. Kernel positioning is 0. Kernel positioning tag is start with 0. Kernel positioning, so controller has kernel positioning tag initial at 0. You can do that. But this also, why you not updating it? Position tag unsigned. What is this? Kernel positioning tag. How can this be? Kernel positioning tag. Address size, and these are just generics. I think it got stuck. I will just restart it. It happens sometimes. Okay. Kernel positioning tag starts with 0. Kernel positioning tag starts with 0. It's not just regular signal. It's important signal. Okay. Can you please fix that? What happens if I change this one, sorter, retake, interface, new, okay, new is defined, new is not defined, like this. This is just okay. Let's see if you updated the name. If name is updated and the number is still that huge number, then the problem is somewhere else. Can position new, so it updates it. It does not start with 0. It does not start with 0. Why? This is out. Okay. This is out. Kernel positioning tag is out. Kernel positioning tag is out. Kernel positioning. Kernel position is 0. Okay, let's check other signals. Let's just forget. And why filter mode is this? There's not one. I should just fix that. Start. Yes. Maybe that's why we didn't start everything. Controller. All the things. No. Why? What happened? Controller. It's here. Controller. Where did my controller go? Control. Where is the controller? It disappeared. Start is 1. Did I do that? Yeah, now kernel positioning is now changing because start is 1. Start is 1. Let's see important signals. This is important. Sorter. Okay. Why? Because image from bram we cannot. We are not taking the right bram data. Let's see. These are generic values. It's not important. It's not important. It's not important. Not important. Right. Not important. Start is 1. Okay. We are not giving the address out. Why? Let's see. Scope control. Current control state. It stays in idle, I imagine. Address out is 0. Center address. Okay. It stays in the idle. Stays in the idle. Let's go to the source controller. It is idle. Controller state. Controller state doesn't matter. We don't use that. Scope controller. Controller. Which state? Controller. Current state. Kernel center state. Kernel center state. It changes. It changes when kernel state positioning. This gives the address out. This doesn't do anything. Empty case. Okay, kernel state changes. Center address stays the same. That's a problem. And maybe these two ifs should change places, because obviously they are different things. These should be registers and they should change with the rising edge clock, but this is our condition. If otherwise, we can only write the register in rising edge, but we are also checking the condition and it causes problems. Let's check what will happen after this. I'm doing this. I will do this and try again. So I checked it, that wasn't a problem. I tried another thing. So these were in the wrong direction. It was smaller, it should be bigger. Now I have seen that the timer in controller is not updating. So also you can see that for every clock cycle, let me add controller kernel state. This kernel state should wait for 2 clock signals, as I mentioned many times, because bram cannot give the information right away. But as you can see, it changes in 1 clock cycle. So I was wondering why it is that. So the timer for kernel tag is a variable, and I am just put that timer to test and see if it is actually changing. As it turns out, it does not change. So this should I am changing every timer for kernel tag to timer because maybe it should be signal rather than a variable. Let's see that. Let's see what will happen. Let's see. Now let me check if any is this any left, any variable left. Yeah, yes. What else? Okay, let's run the simulation again. What I need to check is control timer and control kernel state. Timer and kernel state. Still 0. It shouldn't be 0. I will analyze the code again and try to find out why. I'm stopping right now. I come back. I fixed the I don't know if I fixed every problem, but I fixed the problem. The simulation got stuck. That's why I changed the controller's component name. At first I tried to change just single signal's name to timer C, but again in the scopes, in the objects, I still was seeing timer and not timer C, but timer was actually commented out. So I become sure that the simulation is actually stuck. So I tried to restart my computer. Again, it didn't work. And then I tried to change the component's name, and then it got refreshed finally. Now I can see some stuff. I didn't check it yet. I will check. But so what did I change? I changed the rising edge clock position, this if else condition. Now it checks the timer C, then if at the rising edge clock it registers are updated. Otherwise it won't work, and they are not the same thing anyways. So let me check. I will delete unimportant signals. As you can see, now kernel position tag waits for 2 clock cycles. You can see an output, but we don't know if it is the right one. What is this? Image from bram. This is the data come from memory. I will change the color later. This is the address out to memory. So write bram it out, doesn't matter. Controller, sorter, bits. Image bit. What is image bit? Image bit is the output. We don't see the output. That's a problem. But we see the output array. How is that possible? Let me check the sorter. Image bit. Let's check image array sorter. Let's check image array sorter. We have image array sorter, but we don't get to see image bit. So let's check the cases. Current sorter state. Maybe that this isn't updating. Delete. But we see this. What else? We got the sorter, we got the memory interface, we image to array sorter. Again, okay. Image to sorter. Let's change it all to unsigned decimal. And This is sorter state. Sorter state becomes sorting ready. It becomes sorter ready. And we Buffy sorter objects image bit out. Why we don't see image bit out? Because filter is somehow undefined. I don't know why. Filter is not defined. Top bench filter mode. Okay, that was my mistake. Okay, now we can see the image bit. Filter mode still undefined. Filter mode top Testbench filter mode sorter filter mode 0 0 0. Filter mode. Okay, we got this. This is data from bram. We give the address, for example. We are giving the addresses right, you see. No, there's something wrong with this 5 6 7. Let's check it. Controller time receive 5 7 9 11 see, this is the problem. Bigger than okay, check it. 4 5 4 5 6 4 5 6 4 right, and 5 right, bottom left, and 11 time plus 1. If rising is time plus 1, address of this center address. This is right address, center address plus 1 address size. Okay. Why? Bottom left. Yeah. 6. If this, then else. Center address. Why center address is center address init? No, this is yeah. I think it got stuck again. I will check it. Okay, I think I fixed it. Again it got stuck. I don't know why. Maybe the problem is I don't know where the problem is, but simulation gets stuck. Now I have another problem. Timer A. I am using timer A, but sometimes timer C. No, only timer A. So 4 to 5. 4 to 5. 9 to 11. 6, 7, 8. Yeah. It's normal. Timer should change. Timer should change with the clock. Why it waits for 2 clocks? Timer A. Otherwise it won't change. I don't understand this. Okay, I will give a break now, but I think kernel position tag works right. It waits for 2 clock cycles. And then goes to the next. Kernel positioning tag is given right. So this is something. Okay. This is image from, and this, and we need the check address. So for example, we give the address here, and after 1, 2 clock cycles, we get the signal. No, we give the signal here, 1, 2 clock cycles, and we get the signal. We give this address 1 clock cycle, 2 clock cycle, we got the information. Let's check our core file. Make it unsigned decimal 200. Yes, see, it's correct. And let me check if we are giving the addresses right. Unsigned decimal 0, 1, 2. Yeah, let me check it. We have 360 amount of rows, so this is 0, 1, and we started with this. We started with 261, isn't it? Central address. We started with center address index. So we started with this one, evet. Yes. We got 0, 0, 1, 2, 360, 365. Yes, it's correct. It works right. And after that, does it update? It does not update right now, so that is a problem. For example, this one should be 1, but the center image is not updating. That's the problem. We should change update to center. Let's make it sure. Let's see it actually. Center of this image. Let's check it. Yeah, you see, it does not get updated. It should get updated in adjust stage, and we have it reaches adjust stage here, and comes this, but it does not update. Does not update. I'll give a break and then find out why. Bye for now. I find the problem why this central image is not updating, because I make the conditions wrong again. It was like this, and I changed it now. Also, by writing the code this way, it looks more cleaner, so I did that too. If we reach the end, we don't need to do the cycle again also, so that's the same thing for now. So central image is updating, and from the, let's look at our circuit. This address in is updating, and addresses are given by depending on this central address. For example, let's check. For central address 362, we gave the address 123 361 360, because again, for this reason, this is 361 360. This is, we have 360 rows, so with 0 index, this is 359, this is 360, and this is 361. We started with 362. We started with 362, so we are dealing with this square. This is 1, this is 2, this is 3, this is 362, this is 361, this is 361, 362, and it goes like this. This is 721, and we do that for this address also, 363, 2, 3, 4, 360, 363, 364. It goes like this. So the addressing is right, and we also wait for 2 clock cycles after we gave the address. We gave the address, and we wait 1, 2 clock cycles. You see there is a small delay. After 2 clock cycles, there is also a delay, and we take the address here. We always take the address in rising edge, not in controller, in memory interface. We take in rising edge. In this stage, in this clock cycle, we take the image bits here. Then we gave the second address, and we wait for 2 clock cycles. Since position tag is not updated, memory interface won't go to this case, so it's even though this changes, it is not our array image won't be updated, because this kernel position tag is not updated. And then we gave the second address, we waited for 2 clock cycles, there is a small delay, and at rising edge we update we fill the second index with this image bit result, and it is here. Image array to sort. This is field version. First it takes 194 and 165, 162, 184. This is happening in memory interface module. We are collecting the 9 datas around the central address. Then that 9 data is given to the sorter, and sorter will sort. As you can see, it is. I was thinking about it if it can happen in 1 clock cycle, and it actually does happen in 1 clock cycle, so it's a good thing. This is our unsorted image sent to sorter, and this is our sorter image registers. First, we initially give the same array to our sorter registers. Then, after 1 clock cycle, it is sorted. See, this is not in order, but this is in order. And then, since our filter mode is 0, we are using minimum filter, and we are taking this image bit to the output. This is output. And then, after all of that, we go to the next central image. This was for 362. And this is for 363. Starts at here. So we give the output. Then we are giving this central images addresses, right? No, this we are it finished. Now we are dealing with this 2, 3, 4. This is the center 363, and after that image array to sorter is filled with new data. It is given to sorter, and sorter will sort, and our image bit is ready. Seems like it is the same, and does that for other central image bits. For 366 it is different. I mean, for 365 it is different. Array is filled, array is sorted, and image bit is given when the sorter is three hundred 61, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 5, 6, 3, 5, 6, 7, 5 6 7. This is for 366 and the result is given here. So this is 365's filtered out image. So this has to go to 365's position. 365's position. We must take the center address image to this unnamed module. We give this and we give the sorted. We will give the sorted image bit, and then we put this address. We place this result to this address, which we are first dealing with. Let's say image builder. Image builder. We will need clock. We will need center address image, center address. We need this generics. This of size -1. What else? We need image bit. Image bits. We need clock. We can say build ready out. What else? Image tag. We don't need kernel position tag. So can also make a counter. Builder counter. Just as I worked with sorter, like we need sort memory interface ready signal for sorter to be ready, we would also do the same for builder. We can say sorter is ready and then it will work, but our sorter ready works in a opposite way, I guess. So memory interface ready works correct, but sorter ready is mostly ready. how should it be? Like it should give at this stage and be 0 at the other stages, like for 2 clock cycles. We can collect the data after 1 clock cycle from the sorter, but if we do that, it will mess up the order, because although the sorter takes 1 clock cycle, the other stuff does take more than that. For example, taking data from bram, it takes a lot of clock cycle, like this amount. This amount. So maybe after we are updating the central image, we can say now the image builder can start, like this at this stage. Let's take when this is updated, it can start. But if we say that, then obviously it won't work, because image bit comes out here. This is adjust stage. This is adjust stage. After adjust stage, yeah, maybe image bit comes here. This is tricky. This is the center image, and this is the result. This is our adjust stage. It is updated in adjust stage. It's given to sorter. It's sorted out, and after 1 clock cycle and 2 clock cycle, image bit is ready. Also in a falling edge, we can collect this here. I can put a timer, since it will be all same. It can take data it can, for example, take this kernel position tag 11, and when 11, it can count 1, 2, 3, 4 clock cycles, and it can take the center image, and it can load after 1, 2 clock cycles. It is possible, but it's I believe not a good way to do that. There should be a better way. Okay, let's do it. These things had to be thought before starting whole thing, because for example I need another stage for that, not just adjust, for example build stage, and at that build stage all things should, for example, stall, and then I can build and then I can start again. But now I have to find a solution for the problem, and now I have a problem. If I put an adjust stage now, I don't know what will happen to the other stages, so it will be very confusing to fix the situation. Now that's why building the same thing twice often, I believe, a good practice, at least for me. So I will also need kernel position tag from controller. This is integer. Let's also add the start signal here. after start is given, after start is given, control break starts. Is there a wait? Should I wait after? When does the kernel positioning tag is given? Kernel positioning tag. This is the thing I'm looking for. So ready starts is given here. What is this? And after rising edge clock, we give it 0. So after starts and rising edge clock, we can take this kind of positioning tag, and also we can take center address integer. Center address integer kernel positioning tag. We don't need kernel positioning tag now. We are just checking if kernel positioning tag is 11, which is arbitrary random number that I picked. If 11 is after 11 is given and 2 clock cycle has been passed, we can take this result and take that result to this address. So what we are doing now is, after ready, we can go to this next stage. We can also take this center image, center address, center address, build. Okay, so each center address is integer, isn't it? It's integer. So I'm changing this center address. This can be out. We can also take center address int, which is integer. Center address integer. Okay. This should be integer. Is now center address integer. Oh no, this is wrong. This is wrong, because we can make the start off at some point. So if rising is clock, we can do this. There is again another problem here, which is we are waiting for 2 clock cycles now. but it is not a problem because central address integer stays there for very long time, so we can take at this clock cycle, at this clock cycle, at this clock cycle. It doesn't matter. Also, we would like to take it, for example, at 0 kernel position tag. Maybe after 0 we can wait 1 clock cycle, 2 clock cycle for this case to change, and we still have the same 1, 2 clock cycle, 3 clock cycle. We can now take this. Case is changed, now address is stored. Okay, it is doable. So we can check if signal it is just same with kernel position tag. Almost always. If kernel position tag is 0, then central address hold is that, and we can now change the state. Waiting for switch. I make the same mistake again. If rising edge clock should be here. What else? Waiting store. Now. If kernel positioning tag is 11, and now we have a timer. Timer builder. If rising edge clock, then if this timer can be incremented, and if timer builder is larger than 1, 2, 1, 11 is given at rising edge. Does it increase? I think it increases. It becomes 1. Will it increase? It becomes 11. It is this. It's a rising edge, so it will increase, but we will see that result after the rising edge. So timer for builder is 1 at this position, so 2 at this position, 3 at this position. and the result is here. 0, 1, 2, 3 at this position. So we should take the data when the kernel positioning tag is 0, I guess. Kernel positioning tag is 0, we take the data. Kernel positioning tag is 0, we take the data. We take the data, but we are using the previous addresses. This is the address. We can take the address at 11 and we can take the result at 0. Okay, that's better. How about the initial stuff? We can take the address at 11, I said. So we can start the kernel position tag with 11. Yeah, kernel position tag when 11, we can take this what? 11 we can take the address. We can take the address, center address integer. Okay, now we can store that in builder module. When kernel position tag is 0, after that we don't need this, I guess, now, because when it is 0, after 1 clock cycle at rising edge, we can take this 362. If it is undefined, then we have to wait for 1 clock cycle. 11, after 11, now we are in waiting for sortie stage. Now we are in waiting for sortie stage after 1 clock cycle, but this is not 0, so we wait for 0, and when 0 happens and it's rising edge, no, we should wait. We can do falling edge. At falling edge we can take the value. This is 0. We can take this image bit. Where's the image bit? We can take the image bit. Image bit holder. Single image result holder. using full edge caused problems. So maybe I should use timer. I didn't define this right. Result of this bram that says What's the problem? What's the problem? What's the problem? Yeah, this is we need to make it to unsigned STD logic. STD logic vector to unsigned, and the size is I'll just size to unsigned address size to unsigned. It is maybe unsigned. Oh, I didn't add the numeric library controller numeric. Yes. Store the address. Store the address is also integer. Current builders image result from bram. Image result holder. Image result is not image result to bram. Image result to bram. It's STD logic vector, but image result holder is image bit, and image bit is STD logic vector. Image bit is not. Is it STD logic vector? Yes, because the builder has it. Builder takes it as a STD logic vector. This takes it as a logic vector. So this also takes it as STD logic vector. So this is STD logic vector. Okay. And it goes again to this. I will add this in here. No. I will give a bathroom break. Okay, I'm back. Let's add this in Testbench. I forgot this ready signal. Build ready. Why not? Build ready. What is this? Build ready. What's this? What else? I don't need this. What else? I also didn't add this build counter to build counter. Oh no. Okay. Build counter, build counter, build counter, build counter. Build counter in terminal. Declared. It is very much declared. Which one is not declared? Build counter. This is build counter. Build counter. Build counter. Oh, okay. Okay. Build counter. Which one is not declared? Okay. No. Image bit. Center address. Center address in it comes from controller, obviously. Center address out. No. This. Is this integer? Address out. Yeah, this one. It's this one. Okay, image bit comes from sorter. Image bit results. Comes from sorter. Center address init. center address in it. Is it an out signal? Address out, kernel position tag center in it. Controller doesn't have center address out. Just out. The STD logic vector center address. We don't have the center address out. Center address. We update it here. Center address in it. Let's make it an out signal also. Center address out. Center address in it. Out. Just logic vector. What is this address out then? This is to the bram. To the bram, and circles the central kernel, central position. But this goes to the builder and just center. Okay, you have to change it. Oh. Address out to start. Address out starts. This one. Okay. So we need to define the center out controller. We must define that signal in Testbench. Signal bench. The logic vector address. This is an address. Okay, so we are doing that, but we didn't do controller signal. Is there something wrong? Of course that's wrong. I didn't finish it. Center address out. Center address out. Center in. It's not integer. Anyway, I'll change it. Center address it. When it is updated, we can say center is out is actually same as same. Oh no, center address out is taken when center address, when kernel position is 11. When kernel position is 11, we take the address. So we will also make this 11. We will also make this 11. So we take the address at 11. So address. So we can do that in here. Center address out can be now same as this. This is an integer. Why I make this integer? Everything's right. Everything's right. I missed something. I am doing what wrong? Okay.
The moment of truth. Will it work? Build ready. Let's change it here. How about this one? Build ready. So let's change that. It comes build already now. Okay. Component, and we will change it in here also. This is build ready now. Okay. Okay. Something are not right. Oh, I am trying to give the address to Bram from image builder now. This address out is to Bram, and it should be center address in, isn't it? Center address. This is center address in. It's a huge mistake. This is in. Okay. Let's add the objects. This is an important This is an important object. This is an important object. This is an important object. Clock is obviously an important object. Okay. What else? Controller. Camera position state is important. Address out is important. Address out. Okay, camera position tab. Center address is important. Okay. Bram data out is important. These two are related. These three are related. This is important. I want to see this. Bram, this is important result. Result, Bram, this is important result. I also want to see if these states are working. What is this signal if it doesn't work and all other things working? Sensor address. There's no such signal anyways. What is this? We don't have the signal. Just delete. Yeah, we need this. Not this. This is to Bram and this is to image builder. Okay, try it again. It looks good though, simulations. Okay, it is updating. For this, for initial, our center is 362 and we are taking the wrong address. That's a problem, first of all. this should be 362, but we are taking this. Why? Because it's about this. Center address should be center address this. Okay. First signal may be undefined. Let's see. Yeah, we can't see the first signal. The center is 362, but we are taking 363. Why? Because for 364 we are taking wrong address. When are we taking the address? In which stage? Let's see. Image builder. We are taking the center address in it. In store the address stage. It's the stage builder ready. Store the address stage. Why it is store the address stage? At kernel position 11, which is kernel position 11 is adjust is here. No, at 0. At 11. Let's check. Kernel position tag. Yeah. You can delete this. When it comes 11, we are storing the data. Store the address. This is idle, and it comes store the address. Let's see. Builder objects. Store the address hold. Does that work? No. Store the address at the end of store the address and at the beginning of waiting for sorter. What would happen? At least this is changing in right direction, but it gets this. Center address init, center address init. That center address init comes from controller, I believe. Yeah. And sorter address. Sorter address. I will check why we cannot take this address. And then I will come back. Bye for now. I found the problem again. It was the simulation. I'm doing something really wrong. Maybe I'm not. Why it is not updating? I don't know that, but it's not updating. Even though I restart the whole Vivado, it does not get updated. It only get updated when I change the component's name. I started with controller, then it became controller A, B, C, D. For every kind of problem, I changed the component's name, and magically, simulation is updated. Now, I didn't change the code, nothing. This should be center init, not center init +1, because it is updated not in the stage after rising edge. So this should be that. Okay. This is our center image init, and after this whole sorting process ended, until the whole sorting process will end it, we can say that this is our address, and that
and this is our image bit which came from the sorter. I'll continue later. Okay, so last time we noticed that there is a simulation mistake, and but we didn't check if sorter is doing his job right. So we will check that if sorter check doing his job, and builder is giving out the right memory address and right image result from minimum filter blurring. And then what we have to do is take that image bit for every single address and write them into a text file so that we can turn that to an image and test if it is similar to our original image, which is this. This was the Koya file we uploaded to the block RAM. Since we are not dealing with, since I am not dealing with FPGA, this is just arbitrary. We don't actually uploading to block RAM. We are just assume there is a block RAM. Unnecessary details. So let's check the simulation again. I will delete unnecessary signals because they distract me. That's it, all of them. So what we need is obviously clock. What is important? Are we giving the center image rights? Are we giving the right address out to the bram? which position is that. Maybe that's nothing, but we can understand by others. That's unnecessary. So we have that. So the sorter doing his job right. This is the registers inside the block RAM, inside the sorter. This will give out something, and maybe we might want to check if sorter ready. What else? Sorter controller. Then we have to build that depending on the image bit, and image bit also comes from sorter. This is the image bit also. Sorter ready, image bit, image array in the sorter, builder. Am I recording? So builder will take this image bit and give it to block RAM address, result address to bram, image result bits. Okay, and maybe builder ready. Let's check. These are our results. This is our center image. This is sorted array. This is the addresses around. For example, we started with 361 and we are giving the addresses around 61, but not here. We are doing it here. We are doing it here, and we collect every bit and fill every bit to a register, which transferred through image array. It's a std logic vector array, and after one cycle has finished, it is actually loaded into builder, then it is sorted in one clock cycle, which I still don't know how, but yeah, it can happen in one clock cycle, and it is sorted. Then, since our filter is minimum filter, we will take this bit and send it after one clock cycle to the image bits register of the what builder. This is, as you can see, builder, but not in one clock cycle. It is given as an output here, and it is stored here. Okay, let's check if there is any slide, so everything is doing in right time. After one clock cycle this happens, and after 1, 2, 3 clock cycle this happens. This happens after one clock cycle. This happens 1, 2. I will always count from the rising edge. So 1, 2, 3. Okay. From to this 1, 2, 3, yes. So 165 and is loaded into 361 address, and it will do the same for this, it will do the same for that, it will do the same for that, until we will reach the last column. And we can't continue after that because we don't have padding. If we had padding, then we could have done that, but at this time, if we want to access the next column while we are at the one column before, then it will give it an error. It will cause problems. So we are almost finished. What I want to do is to check if this will give the correct image. Since I don't have an FPGA right now, I can't check it. But what I can do is write this address and this bit to a text file, and then I will use my library module to transform that to an image again. Before I start recording it, I researched how can I do it, because I haven't seen any example of VHDL that can create a text file and fill a signal's result in, for example, rising edge clock. I didn't see any example of that, but I have seen that in Verilog. So what I must do is create a Verilog Testbench which wraps around our main Testbench, and we can drive a specific signal and write that to a text file. That's the only way I can think of right now. Maybe there is another one, but I don't know. It's not a bad solution also, so there's no need to be too picky. We won't be giving any so we need register integer f register what clock register clock register f. Do we need another thing? No, it's enough. We can parameter clock period, which will be 5. Initial initial clock will be 1 binary 0. Always clock will be clock always, and after always clock periods. Initial there will be always posage what at posage begin and at when at post edge, let's see, post edge builder ready, for example, builder ready, this will be new Testbench will be do we have any input? Let's make it let's make the clock same as this clock. This would be input. If this would be input, then we can clock v equals the same clock of the Verilog. But okay, this is not in always, this is outside. This is now unit on the test, builder and builders, builder ready, I wanna check if that works first. Hello there, and clock, this will be clock begin and in F right F open. I will check the syntax and I will come back. Okay, I think I get it. So initial clock will be updated, and that clock will be the input of the main Testbench. We will open up this file, but we won't write it now, and we close it after the end of simulation. I am checking if I can reach this signal, and if it reaches I can display something. Let's also display, for example, image bit, as we want to figure this out. Builder image bit. Let's say builder image bit. This will be decimal. What else? I also want to know if we are getting which address, which result address bram, results address to bram. Let's make it so we don't need it. Let's keep it. Maybe this won't give any result. So there should be line break after that, and what we need is, I also want this here. What separate this by this. Okay. Let's say if we can write anything. Write F. How was it? Will it work? Right, like this. Let's put a line break. Was it like this? Probably. Okay. Let's check it. And what we need to do is set a stop. Okay. What is the syntax error? What is the syntax error? What do we need? Display. Error near display. Okay. Okay. Now run simulation. We need to close it first. We will check two things: if we can display after fixing the error. Support. Builder ready. Let's change this to Verilog this to Verilog. No, whatever. Simulation sources, Verilog Wrapper. I'm trying to access this, but I cannot. Builder ready. Is builder ready an input? Builder ready. It's an output. Builder ready is an output. Builder ready. I'm trying to access this one. Why it won't work? Builder ready. It's on the test. Builder image bits. Builder ready. Oh, it's this, and I am trying to access some random symbol. Maybe I hope it will work. Let's see. Yes, it works. Okay. What about other things? Clock. Verilog clock. Shorter. Builder. Image result. Builder address. Center address. Control center address. In out. Okay. And did we get something really messy? Why? Because I write the line break wrong. So this should be like this. No, this. No, the other way. This. And this should be this. This should be this. Run simulation again. And did I create the text file and did I write it? What's the text file? Verilog outputs. Why? Why? What is this? What is this? I think display already gives a line break. Let's check. Yeah, display already gives a line break. So what I want to do is this, take this, copy this, like that. And delete this. Write this like this. Okay. I will come back. Okay, so that should be F right, not right. And I fixed that. What did and let's check if Verilog output is failed. Verilog output is failed, but how much? How many? What are these? These are image bits. These are image bits. So the blackness value that we talked a lot of time ago, between 0 to 255. But we need and this is also blurred results. Blurring happens with the Verilog VHDL logic. If I had an FPGA, that would happen in FPGA logic. But now it's just simulation of an FPGA logic with the VHDL code. So I achieved to extract these values from the code. That's something. That's a good thing. But it should be. Let's remember our image dimensions at the first place, which was 265 to 360. It should be around 265. It should be like, we have an image code, we can test it with this. How many bits do I need? It's 2,000, 95,400, 95,400. What do I have? It's, which line is it? It's like 177. Why it is that? It's probably because the simulation ends very early. When does it end? We can check it. We don't need to erase there. Let's check it. Builder ready, builder result, builder address, builder counter. No, this distract me. Controller center image. Let's check. This fails again probably. I am guessing this will be like 178 or something. What? Center image. So there is another problem. I am closing this file. I have to close it, but it closes before even the simulation has ended. So that's the second problem. One, I will have to extend the simulation time. Second, I have to close the file in the right time. So yes, there's no problem. This should be like this. Okay. When should it end? How long should it last? This is 5,000 nanoseconds, 50,000 nanoseconds, and it only counts to 1/10. So it should be 10 multiple of that. simulation settings. Let's make it this. Hope that it works. Apply. Yes. Start. Okay. What else? What else? This should be closed. It's this. It's the same number. It's a nanosecond. Okay. Just to make it sure, I will close the simulation first. Then reopen it. Okay. What we have done is, again, I described it at the beginning, but we take the blackness value of the blackness value of the addresses around our center bit, and we take the minimum value, and we take that minimum value as an output of that central address. What we have done is blurring. How we did it? We did it with very description language, VHDL. We did it with VHDL. Let's check if that will work now. Let's change it. Final, hopefully. Okay. And this was our circuit again. Like blocks, design blocks. Okay, simulation continues much more. Okay. Okay. Is that all? What is this number? This number is, this is the image bit, and this is the address, and by I believe we need more. We need more. I think we need more. Let's see how many bits did I get. This was this. We extended simulation by 10 folds, but we are getting only double amount of bits. I don't get that. I didn't get it. Let's increase it more. We double it. Let's make it 5 and one more 0. That should be it. Okay. 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 the thing is what will happen at the edge of the boundary. That's important. And we also skipped 360 bits also. The design flow, it's a design flow. I should have think about the padding beforehand. Now I can't just simply add 0 to the padding. It would be too complicated. Okay, what happened now? I think it's not enough. Let's see. No, not enough. Not enough. Oh, what? How much do I need? How much do I need? It's too much. It feels like too much. Okay. 95402. 95402 is what? Okay, what is the output? So that's let's look at that. Let's look at that. What is this? Why? What is this? Let's just forget about writing. And this, we are already displaying it. This is our image bit and this is our address, but this is our address bram. We are getting 2 values per one ready signal. So we should just wait for one more clock cycle. I mean not one more clock cycle. We should just wait for the post edge for ready signal. Why is it so hard? It's so hard. Just wait for one ready signal. Okay. Post edge. How should I write this? Post edge. At post edge. This way. Okay. And I didn't like this order. So it should be here. This should be here. Okay, and we need a comma for comma. We need comma. We can do this. I believe we can. Okay. Transformation again. Okay, so now am I skipping address? No, it's correct. That's correct. I will also check if I'm taking the right image bit, because maybe I'm not. Maybe I'm taking one image bit before or one later. Okay. Do I have to start simulation again? I hope not. So what I need is image builder. I need image builder bit, image builder address. Okay, that's enough. And let's also not forget about center address image out. Okay, and clock. Check. Oh, it starts again. Let's check, by the way, the output. At first I was just angry why the simulation takes so much time, but it turns out it also calculates like power consumption, combinational delays. So we are building something really big, and it calculates every transistor's power consumption and combinational logic delay. It is reasonable. It's even fast simulation when we think about all of the aspects of it. So for example, for 361, I need to get 165. Let's check the of that one. Simulation Verilog output. Let's check. Yeah. Let's open that one. Open that with Visual Code. Okay. For 300, there's no padding, so okay, I will add that 361. Then I have to get 362 for 1, 2, 3 signals. I need 162, not 4. 1, 2, 3, and then I will get 149, and then just after that I need 1, 2, 3, 164, 1, 2, 3. Yes, it's true. It works correctly. Now, did we reach the limit? Yes, we reached the almost reached the limit. There is a last column limit. There's a last column limit, isn't it? Let's check. Controller does not get to next stage if we have this boundary conditions. so it won't go certain past certain addresses. That's good. Again, we skipped first 361 bits because I didn't think about it, so I will fill it with 300 for 360, just a random number, just to check if the simulation, if the code works right, and can we see anything resembling this image. I will be even surprised if I just see something like this. I will be surprised. Truly. So I need to go to until this should be 361. 161. They should mistake. That's the mistake. 360. 360. One more. Yeah, exact amount. This should be also same as, maybe not. One more. How much should it be? Let's check it, the original image. What I'm doing here is filling, padding almost black to the boundaries. Nothing really affecting the image. We won't be able to see that probably. How many do we need? We need 95400. 95400. 95. We skipped a lot, I guess. 95. Why? We skipped a lot. Anyways, I don't know why. Skipped a lot, I guess. I don't know. Five, 4. I would like to also add this just to make it same. Just to make it same. And one more thing, I want to make it this. Let this end. 95402 950. Okay, how is it that add too much? I feel like I added 2 columns. I feel like I had more than 2 columns. How many columns? It's like 1000. Feels so much. Feels so much. Wow. Okay, what can I say? Let's check it. Let's check it. What was the name of its output? What was the name of it? Okay. This, so I would take this here, copy, what, no, rename, copy, Verilog, output, copy, our code here is this, Verilog image output. It won't work. if it works, it's a miracle. It's a miracle. The shape, did I adjust the shape? No, don't do it. What's the shape? Okay. File not found. How can you find this? This does not exist. This is wrong. Okay. Image is saved. Let's see. What? Oh my god, it works. It works. As you can see, it works. Amazing. Let's check if how blurring happened. Is it really blurred? Yeah, you can see, as you can see, let's make it 100. The details of that mountain seems to disappear. Details of the shore has disappeared. These rocks obviously disappeared. Also I added too much columns. I need to adjust the boundaries more accurately next time. Also there is, yeah, you can see there's a problem with the right edge, but other than that, even for this amount of success, I say it's really amazing. Okay, what we have done so far, let's recap. We find an image, then transform it into a one-dimensional array with the modules that I have written, and then I transform it to an image with the same module to see if anything's wrong, and nothing was wrong, it was correct, except this black dots. Then I started to write VHDL code, but before that, VHDL code is another program, is not a like regular programming languages, so we have to first think about what are our inputs, what are our outputs, and how they will be changing with their relation to each other. So you have to will write some kind. We have written some kind of block diagram. We in more high level abstraction, it's a we add control module, memory read, this is bram, this is bram read, this is bram write, this is memory interface, which we gave the address from the controller, and that address's result will be written to memory in memory interface register. After 9 registers are filled, we will send that 9 data array to sorter, and sorter will sort in 1 clock cycle, and it has other functions. We selected minimum filter to test it. Then the sorter will give one image bit for one address. That address is the same as this address. We didn't add that, we should add it. We should add it, not in here. Okay, I will add it later. And the image builder will have the image center image address and the image with result from the sorter. Then we'll write to the bram. Bram is a block RAM. What controller is doing is circling around the center image and updating the center image, also checking if we have reached the boundary, upper bound. There should be an upper boundary, lower boundary, and right and left boundaries, but for the simplicity you can ignore right and left boundaries, but upper and lower boundaries are important because you are trying to access the information that you don't have in the memory read registers, bram. So we draw that diagram. We think about how the address relation happens and how we can sort. We created separate modules for every kind of block. We created a block design from IP integrator. What it does is creating a wrapper to easily access the bram inside of an FPGA, but I didn't use FPGA, so that's just arbitrary registers. We also write the controller module, sorter module, memory interface module, image builder module. What was the important thing in sorter register is the writing of selecting the sorting algorithm. Sorting algorithm that I picked is, what was it? Selection sort. I discussed the reasoning behind it. I assumed the reasoning. This wasn't my internship project. At the end, at the last day, our advisor advised us to use selection sort algorithm. I have some opinions about that. I discussed it before. Other than that, then we have I explained we have to add a Verilog wrapper around our main test bench, because I cannot access and write a signal's result to a text file with VHDL code as I know, but there might be for some way, but I don't know. So I created a Verilog wrapper. I write the results to a text file with that Verilog file, and then I checked. I manually added the boundaries. I manually added this boundary. It is visible. Upper boundary is okay, but lower boundaries not correct. I added black, this black line, and then I transformed my output from Verilog to an image. I transferred that to an image also with the module, Python module that I created. Okay, that was all. Thank you for listening. If you are still there, it was a long journey. Okay, bye for now.